Hello and Assalamualaikum everyone. My name is Dina Rainisa, and in this video, my group will be presenting on our group project titled Brain Tumor Classification Using Convolutional Neural Networks. So this project is part of our exploration into medical image analysis, where we apply deep learning techniques to improve healthcare, specifically for early brain tumor detection through MRI scans. Deep learning is playing a big role in the advancement of medical image analysis, and one of the most powerful tools used today is the convolutional neural networks, or we call it CNN, which is good at analyzing visual data like medical scans. In this project, we focus on brain tumors because detecting them early using MRI scans is critical for saving lives, as it helps doctors diagnose faster and more accurately. So we developed a CNN model that can classify brain images into four categories: glioma, meningioma, pituitary tumor, and no tumor. The main objectives of our project were to automate the detection of brain tumors from MRI images, to improve the speed and consistency of medical diagnosis, and to demonstrate how CNNs can be applied in real-world healthcare situations.
Assalamualaikum, my name is Nur Zafira Alia binti Naushizarin, metric number 2316126. So, today I will be presenting about the dataset we used in the assignment. The dataset we use is the brain MRI images for brain tumor classification, publicly available on Kaggle. It originates from research by Cheng et al. And is widely used for tumor type classification. The dataset is organized into training and testing folders with 5,712 and 1,311 images respectively. Each has 4 subfolders representing tumor classes, which is glioma, meningioma, pituitary tumors, and another one for no tumor. Images are in JPG format and is either grayscale or RGB. We did not manually edit the images. Instead, pre-processing was handled using image data generator from TensorFlow. It rescaled the pixel values, resized all images to 150 x 150, and applied data augmentations such as horizontal flips and zoom during training. A validation split of 20% was also configured within the training folder. In the optimized version, we added more transformations like rotation, shifts, and brightness control to improve model robustness. More details on the pre-processing data will be explained later by Sister Salsamila.
Assalamualaikum warahmatullahi wabarakatuh. Hi, my name is Yasmin Handani Salsabila binti Muhammad Hakim, and my metric number is 2318740. And today I'll be walking you through the first part of our AI code demonstration, where we focus on preparing the data and building the deep learning model. So we started off by uploading our dataset, which is a zip file containing MRI brain scan images. These images are already categorized into 4 folders: glioma, meningioma, pituitary, and no tumor, both for training and testing. After extracting the contents, we verified the folder structure to ensure that each category was properly loaded. So this is the code we use. This is important because our image data is organized into subfolders where each folder name corresponds to a class label, like glioma or no tumor. If the structure is incorrect, the flow from directory function wouldn't be able to correctly assign labels, which would lead to incorrect training and poor model performance. So checking the folders beforehand help us avoid errors and ensure accurate data labeling before we even begin training the models. The next step was installing the required Python packages, which in our project we need to use TensorFlow, Keras, Matplotlib, and Scikit-learn. Then we need to import the necessary libraries. We use TensorFlow and Keras, which are popular frameworks for building and training deep learning models. Keras provides a user-friendly API for quickly designing neural networks. We also use NumPy for numerical operations and Matplotlib for plotting training accuracy and loss graphs. To handle image data and apply real-time augmentation, we imported image data generator from TensorFlow Keras pre-processing an image. And finally, for evaluation, we use Scikit-learn's classification report and confusion matrix function, which help us analyze how well the model performed across the 4 classes. After that, we prepare our data using image data generator. This step is critical because raw images alone aren't enough for effective training. We need to pre-process and augment them to make the model more robust. So here's how we do it. First, we normalize all pixels by rescaling them between 0 and 1, which is we use this 1/2.255. This helps the model train faster and more efficiently by keeping the input values in a consistent range. Then we added horizontal flipping and zoom to stimulate variation in how scans may appear. These are simple yet more powerful augmentation techniques that help the model become more generalizable, meaning it still perform well even when the MRI scans vary slightly in orientation or size. Then we also split our training data into 80% for training and 20% for validation using the validation split parameter. This allows us to evaluate how well the model performed on unseen data during the training, helping us spot overfitting early. We choose an image size of 150 by 150 pixels to maintain a good balance between image detail and training speed. Larger sizes may improve accuracy, but it will slow things down significantly. And we use a batch size of 16, which means the model updates its weight every 16 images, and this helps stabilize the learning. So here we can see we have training images, validation images, and test images across the 4 classes. Now, let's take a look at our CNN model architecture. We use something called a sequential model, which is a simple way to add layers one by one in order. So first we added 3 convolutional layers, or which is called conv2D layers, which filters sizes of 32, 64, and 128. These layers help the model look at small parts of the image to find useful patterns like edges, shapes, and texture. After each of these layers, we also use ReLU activation, which simply helps the model learn more complicated things instead of just straight line. Then, we also use something called max pooling 2D. This reduces the size of the image while keeping the important parts. So it also helps make the model faster and better at focusing on the main features. After that, we flatten the output, which means we turn the 2D image into a single line of numbers. This let us connect it to regular dense layer, kind of like the decision-making part of the model. We added a dense layer with 128 neurons, which help the model understand and combine everything it has learned. Then we added a dropout layer of 50%, which randomly turns off some neurons during training. This helps prevent overfitting, which means the model won't just memorize the training data, it will help to generalize it better. Finally, we added an output layer of 4 units with a softmax function. So this is because we have 4 different classes, so we use 4 units. And softmax gives us probability for each one, so the model can tell us which class it thinks the image belongs to. And to train the model, we use a Adam optimizer with a small learning rate of 0.001. This helps the model learn step by step without jumping it's too fast. We use categorical cross entropy as the loss function, which is the standard choice when dealing with multiple categories, and we track accuracy to see how often the model got the correct answers. Next, we train the model for epochs. So, as you guys can see here, our training accuracy is steadily increasing and it reached about 88.7%, while the validation accuracy also steadily increased and reached around 78.9%, showing that this model is actually learning well without severely overfitting. So now I'll hand it over to Ami to explain the evaluation result, optimization process, and demonstrate the model in action.
Assalamualaikum, my name is Ami Nuera, metric number 2318436. Okay, now that our original CNN model is trained, we evaluate its performance on unseen test data, which is the 1,311 images the model has never encountered before. We use 2 important tools here, which is the confusion matrix and the classification report. So the confusion matrix breaks down how many predictions the model got right or wrong for each class. So each row represents the actual class and each column shows what the model predicted. So ideally, we want all values to fall along the diagonal, that means correct predictions. So the classifications report gives more detailed metrics like precision, recall, and F1 score for each class. So precision tells us when the model predicted this class, how often was it right, and recall tells us out of all actual images of this class, how many did the model catch. And the F1 score balances both, which is useful when class distribution is unbalanced. So in our case, the model did extremely well on the no tumor class, likely because it's visually more distinct. It also performed decently on pituitary and glioma, but for meningioma, performance drops. That's probably because some tumors have overlapping patterns or features that are subtle and hard to distinguish even for human eye. Next, model accuracy and model loss graph. So this graph helps us understand how well the model learned during training. So on the left, we have accuracy. You can see that both training and validation accuracy improved over time, which means the model was successfully learning from the data. But on the right, the loss graph shows how far off the model's predictions were. A lower loss means better predictions. Training loss dropped consistently, but validation loss flattened a bit near the end. So that's a sign of mild overfitting, which is the model is starting to memorize the training data instead of learning general patterns. So this tells us that our current setup works well, but may need some tuning to help the model generalize better. To simulate a real-world use case, we pass in a single MRI image, which is just like how a doctor might upload a scan for diagnosis. So before making a prediction, we pre-process the image to match the shape and scale of the training data by resizing it to 150 by 150 pixels and scaling the pixel values between 0 and 1. Then, we use model predict to get a probability score for each of the 4 classes, and we take the class with the highest probability. So here, the model correctly predicted no tumor. So this test shows that our model isn't just good at batch predictions, it can also make confident decisions on individual cases. So to improve performance, we created an optimized version of the model. But instead of changing the whole architecture, we focus on the data and the training process. First, we adjusted the image data generated to use more aggressive data augmentation. So this includes random rotations, brightness changes, and shearing. So basically, we're simulating different MRI conditions like lighting or angle differences to help the model learn more generalized features. We also increased the batch size to 32. This means that the model sees more images before updating its weights, which can make training smoother. And finally, we changed the learning rate from 0.001 to 0.001. It makes the model learn faster, but we had to be careful not to overshoot the optimal solution. So all of this was done to reduce overfitting and makes the model more robust. So after retraining, we evaluated the optimized model the same way. The confusion matrix is now more balanced, which is fewer misclassifications on the meningioma and a stronger spread across all 4 classes. The classification report supports this, because while the accuracy is slightly lower, which is at 37%, the F1 scores for all classes are more consistent. This shows that the model isn't just memorizing dominant patterns, but it's learning more evenly across categories. So in real applications, a balanced performance is often more important than just high accuracy. We also tested the optimized model with a single MRI scan. It correctly predicted no tumor. So this is important because sometimes tuning a model can improve performance in one area, but accidentally make it worse in another. So here we confirm that the optimized model is still strong on individual predictions. This chart shows how the original and optimized models compare. While the original model had slightly higher accuracy, the optimized model had more balanced F1 scores, especially for the classes that were previously weak, like meningioma. So that trade-off is worth it when you're working in sensitive fields, especially like healthcare.
In conclusion, we successfully trained a CNN model that achieved 78% test accuracy in its original version and 73% accuracy in the optimized version. The model showed strong performance in detecting pituitary tumors and no tumor cases. However, it struggled to differentiate between glioma and meningioma, likely because of their similar appearance in MRI scans. So some important lessons we learned during this project include the need for proper data pre-processing and augmentation, the importance of using accurate evaluation metrics, and how crucial it is to handle real-world medical data with care. And for future improvements, we suggest using transfer learning models like ResNet or VGG16, solving class imbalance in the dataset, applying advanced hyperparameter tuning, and using larger, more diverse datasets for better model performance. So that's all from our group. Thank you very much for listening.